If you haven't had a chance to draw this, please do so and pause the video. So here we have a graph that does a few weird things in its existence here. It begins its life by increasing, does this max, min, max, does a weird turn here, but then its end behavior at the far right is decreasing. So if you ignore all this stuff in the middle, all right, if you ignore all that stuff in the middle and just consider that it starts by increasing and ends by decreasing, what does that bring to mind? A parabola opening downward. So I expect in this problem an even degree with a negative a. That's what I expect. And it's good to go into a problem before you try to find the a and all the x-intercepts to know what you think is going to happen. That's helpful in math. The best math people know what their answers should look like. All right? If you don't know what your answer should look like, you're behind in the game. All right? So knowing, okay, it should have an even degree and it should have a negative a, that should be helpful. So as we work from left to right, I see what's called a single root at 1. I don't want that. I see a single root at 1. I see what's called a double root at 5, because at that moment, at that x-intercept, it's acting like a parabola or parabolic. And here at 8, there's a triple root because it's acting cubic. If you don't know what a cubic function looks like, x cubed does this. Negative x cubed does this. So right here, it's acting like an x cubed because it opens up and then switches to opening down. So I don't necessarily know that that part's negative, but I know that this root has a cube on it. So as you're working from left to right, doing your x minus r1 and your x minus r2 and your x minus r3, whoops, because how many roots are there? 3. There are 3. 1, 2, 3. There are 3, but that doesn't mean that's what the degree is. Here's the degree. It's going to be 6 because we have x minus the first root, x minus the second root, and x minus the third root, 8. But I'm not done. Because at the first root, it's a single, so you don't need an exponent outside the parentheses. At 5, it's acting like a parabola, so give it a squared to make it act like a parabola. That's what does the trick. Hold on a minute. And at x minus 8, put a cubed because it's acting like a cubic function there. So now when you count up the degrees here, we have x cubed, which counts for how many x's? 3 plus 2 plus 1 for a grand total of 6. The degree is 6. Was our prediction correct? The degree is 6. There's a single, double, and triple all in the same graph. Next, we need to find a. And to find a, you can use the y-intercept if they give it to you, and if it's not 0, 0. Are both of those things true? Did they give us a y-intercept? Yes. Is it 0, 0? No, so we are permitted to use it. So let's plug in negative 6,400 for y, while you plug in 0 for x. You'll see when we do the work why I needed the y-intercept to be so big of a negative number. You're going to be squaring and cubing negative 5 and negative 8. You should get a positive number when you multiply these. And it's going to be big in the 12,000s. You are going to get a positive because we have a negative times, what's this going to be? Negative times a positive, right? Negative 5 squared is positive. Times negative 8 cubed is negative. What do you get when you do a negative times a positive times a negative? Negative times a positive times a negative. Doesn't depend on the order. Still get a positive. It doesn't matter. So you definitely get a positive here. You get positive 12,800A equals negative 6,400. So I picked a nice y-intercept because when you divide, you get negative 0.5. Okay? So was the A negative as we thought? It is. That means that that even degree function, which normally opens up, opens down. This flips it downward. All right. So this one example will lead us to this chart in your notes, which I'd like you to fill in now. It talks about what the behavior will look like. The previous part of this video was on root behavior. How does the graph behave at those roots? Does it slice through? Does it bounce off? Or does it curve when it gets there? This speaks of end behavior. The green is when the degree is an even and the A, the dilation, is positive. Okay, the A is positive. So imagine, if you will, the beginning and end. Forget the bumpiness in the middle. What does this look like? A parabola opening up because it's even and A is positive. The red, on the other hand, starts increasing, but then finishes by decreasing. So it starts uphill, ultimately ends downhill. And that's like an upside-down parabola. No, just greater than. All right? If the degree is odd, it begins uphill, finishes uphill. Kind of like positive x cubed or positive x. They don't change and go the other way, ultimately. They stay in the direction they're headed. If A is negative, it's like having a negative line, which goes downhill. Starts in a downward fashion, ends in a downward fashion. Or a downward x cubed. Starts down, ends down. If A was 0, it would wipe out the whole polynomial.